In Chapter 2, we learn how the reservoir delivers fluids into the wellbore using the Inflow Performance Relationship, or IPR. In this chapter, we continue the journey by following those fluids to the surface through the tubing and choke. We'll learn how pressure losses affect production, introduce vertical lift performance, VLP, and combine IPR and VLP using nodal analysis to determine the well's actual operating point. The companion interactive dashboard lets you explore these concepts by changing key parameters and instantly seeing their impact on well performance. Imagine you're standing beside a newly completed well. The reservoir beneath your feet contains enormous energy and appears capable of producing thousands of barrels of fluid every day. The question is not how much the reservoir contains. The real question is, how much can actually reach the separator? Every barrel begins a challenging journey. First, it must flow through the reservoir rock and enter the wellbore through the perforations. Then it must travel thousands of feet up the production tubing, fighting gravity, friction, and multiphase flow. At the surface, the choke deliberately restricts the flow to protect the well and control production. Finally, the fluids must be processed safely by the surface facilities. At every stage, pressure is lost. Each pressure loss consumes part of the reservoir's energy. By the time the fluids reach the separator, only a fraction of the original pressure remains. That remaining energy determines the production rate. This is why production engineering is not about maximizing one component. A high-performing reservoir means little if the tubing cannot lift the fluids efficiently. A perfectly designed tubing string cannot compensate for an undersized choke or surface facilities operating at their limits. The entire production system behaves as a single integrated system, and its weakest component determines the final production rate. As production engineers, our role is to ask the right question at every stage. Can the reservoir deliver more? Can the tubing transport it? Should the choke allow it? Can the facilities handle it safely? Only when every component works together does the well reach a stable operating condition. This chapter is about understanding that interaction. We will learn how reservoir inflow and vertical lift performance combine, how the choke influences production, and how these elements define the operating point of the well. Once you understand this workflow, you'll have the foundation to diagnose production problems, optimize wells, and make engineering decisions with confidence. Remember one key principle: a well does not produce what the reservoir can deliver. It produces what the entire production system can sustain. That single idea is the foundation of production engineering and the purpose of nodal analysis. Suppose the reservoir has enough energy to deliver the fluids. Does that guarantee they'll reach the surface? Not at all. Every meter the fluids travel up the tubing consumes pressure, just like climbing a mountain consumes energy. By the time the fluids reach the wellhead, a significant portion of the reservoir's energy has already been spent. Where does that energy go? It is consumed by three pressure loss mechanisms. The largest is hydrostatic pressure, the weight of the fluid column that the reservoir must continuously support. Next comes friction, created as the moving fluids rub against the tubing wall. Finally, acceleration pressure losses occur whenever the fluid velocity changes. Although usually small in oil wells, they can become important in high-rate gas wells and changing flow conditions. These three components combine to form the vertical lift performance, or VLP, curve. Think of the VLP curve as the energy bill required to transport fluids from the reservoir to the surface. The higher the pressure losses, the higher the flowing bottom hole pressure required, leaving less pressure available to drive production. This leads to one of the most important principles in production engineering. Reservoirs do not lose productivity overnight. More often, they lose efficiency because pressure losses increase. Scale, liquid loading, smaller tubing, higher water cut, or increased production rate can all increase the energy needed to lift the fluids. As production engineers, our objective is simple. We cannot easily increase reservoir energy, but we can reduce the pressure losses that waste it. Understanding these three mechanisms is the first step toward optimizing well performance, building the VLP curve, and ultimately determining the operating point through nodal analysis. Inside a producing well, fluids rarely flow as a single liquid. Instead, oil, gas, and often water move together, creating different multiphase flow patterns as pressure and gas volume change along the tubing. These patterns are not merely classifications. They determine the pressure losses that ultimately control the well's production rate. Near the bottom of the well, pressure is high and gas remains mostly dissolved in the oil. As the fluid rises and pressure falls, small gas bubbles begin to appear, creating bubble flow. This flow regime is relatively stable and generally results in moderate pressure losses because the liquid remains the continuous phase. As more gas comes out of solution, the small bubbles merge into large gas pockets separated by liquid slugs. This is known as slug flow. Slug flow is one of the most challenging flow regimes because it causes large pressure fluctuations, unstable production, separator surging, and cyclic loading on surface equipment. Many wells experiencing unstable production are operating in this regime. With further expansion of the gas, the flow becomes churn flow, where gas and liquid move in a highly turbulent and chaotic manner. Pressure losses become difficult to predict, and the well may experience severe oscillations. Engineers generally try to avoid prolonged operation in this regime because it reduces production stability. Closer to the surface, gas often becomes the dominant phase, flowing rapidly through the center of the tubing while the liquid forms a thin film along the pipe wall. This is called annular flow. The lighter fluid column reduces hydrostatic pressure, which can improve production. However, the higher gas velocity increases frictional losses, and if the velocity becomes too low, liquid can accumulate, leading to liquid loading and eventually killing the well. This illustrates one of the most important concepts in production engineering. Pressure loss is not controlled by tubing length alone. It depends on the flow pattern inside the tubing. The same well, producing at different rates or gas-liquid ratios, can experience completely different flow regimes and therefore completely different pressure losses. Understanding these transitions allows engineers to optimize tubing size, gas lift injection, choke settings, and production rates to minimize pressure losses, maintain stable flow, and maximize long-term production. In other words, mastering multiphase flow is one of the keys to successful nodal analysis and production optimization. So far, we've learned that pressure is continuously lost as fluids travel up the tubing. But here's the challenge. We can measure the tubing head pressure at the surface. We cannot directly measure the flowing bottom hole pressure every time we analyze a well. Yet that bottom hole pressure is exactly what we need to build the VLP curve and perform nodal analysis. So how do we determine it? Before computers and commercial simulators, production engineers solved this problem using pressure distribution charts developed by Gilbert. These charts transformed thousands of pressure loss calculations into a practical engineering workflow that could be completed in minutes. Although today's software performs the calculations automatically, the underlying logic has not changed. We begin with the known tubing head pressure. Using the appropriate pressure distribution chart for the tubing size and flow conditions, we locate the operating gas-liquid ratio and move through the chart to determine the equivalent depth. We then add another section of tubing, calculate the new equivalent depth, and repeat the process. Step by step, we march down the well until we reach the total tubing depth. Finally, we return to the chart one last time to read the corresponding flowing bottom hole pressure. Notice what we are doing. We are not solving the entire well in one calculation. We are building the pressure profile progressively, allowing the pressure to change as the fluid conditions change with depth. That's why this method provides much better accuracy than assuming a single average pressure gradient. This workflow represents far more than a historical calculation technique. It illustrates the engineering principle behind every modern production simulator. Whether you use Prosper, PipeSim, GAP, or any other software, the computer is following the same sequence shown on this slide. The software is faster, but the physics is identical. Understanding this workflow means you understand how a VLP curve is built. Once the flowing bottom hole pressure has been determined for different production rates, we are ready to combine the VLP with the IPR and identify the operating point of the well. That's where nodal analysis truly begins. Until now, we've treated the operating point as if it were fixed. In reality, it's constantly moving. Every well changes with time. Reservoir pressure declines, water production increases, scale forms, tubing conditions change, and surface operating constraints evolve. Every one of these changes shifts either the IPR curve, the VLP curve, or both. This raises an important engineering question. When production changes, how do we know why? Was it caused by the reservoir, the well bore, or the surface facilities? Guessing is expensive. Production engineers rely on sensitivity analysis to find the answer. Sensitivity analysis follows one simple rule: change one variable at a time. By isolating each parameter, we can measure its true impact on the operating point and identify the factor limiting production. If increasing reservoir pressure moves the operating point significantly to the right, the reservoir is the constraint. If reducing tubing losses has the greatest effect, the wellbore is the bottleneck. If neither helps, the limitation may lie at the surface. Notice what happens on this slide. Improving reservoir inflow shifts the IPR curve and increases production. Reducing lift requirements shifts the VLP curve downward and achieves the same result. On the other hand, reservoir depletion, higher tubing head pressure, scale, or a smaller tubing size move the operating point to the left, reducing production. The direction of movement immediately tells us whether the well is improving or deteriorating. This is why optimization is a scientific process, not trial and error. Before changing the well, engineers test dozens of scenarios in a simulator, compare the movement of the operating point, estimate the production gain, and weigh it against cost and operational risk. Only then is the best option selected for field implementation. Remember this principle. Every production optimization, whether it's acid stimulation, hydraulic fracturing, tubing replacement, artificial lift, or choke adjustment, has exactly the same objective: move the operating point to the right safely, economically, and sustainably. Once you understand how the operating point moves, you understand the logic behind every production engineering decision. Imagine you're asked to increase production from a well. One engineer says, "Let's install a larger tubing." It sounds logical. A larger diameter reduces friction, so production should increase. But here's the question: if bigger tubing is always better, why doesn't every well use the largest tubing available? The answer lies in a trade-off between two competing forces. Small tubing creates high fluid velocity, which helps carry liquids to the surface, but it also generates high friction losses that consume valuable reservoir energy. Large tubing does the opposite. Friction decreases, but so does fluid velocity. If the velocity falls below the critical lifting velocity, liquids begin to accumulate, the hydrostatic pressure increases, and production starts to decline. Somewhere between these two extremes is the optimum tubing size. It is the diameter that balances friction losses with fluid lifting efficiency, allowing the well to produce at the highest stable rate. That's exactly what nodal analysis helps us find. Look at the curves in the center of the slide. Each tubing size produces a different VLP curve, and therefore a different operating point. As the tubing size increases from 2 3/8 to 2 7/8 inches, production improves because friction losses decrease. Increasing it further to 3.5 inches moves the operating point even farther to the right, giving the highest sustainable production. But when the tubing is enlarged again to 4.5 inches, the operating point moves back to the left. The well loses fluid velocity, liquid loading becomes more likely, and production falls despite the lower friction. This is why production engineers never select tubing based on diameter alone. They evaluate every candidate size, generate the corresponding VLP curves, compare the operating points, and choose the option that delivers the highest stable production over the life of the well. Remember this engineering principle: the optimum tubing size is not the one with the lowest friction. It is the one that creates the best balance between friction and fluid velocity. Production optimization is about balance, not extremes. We've reached the point where everything comes together. Throughout this chapter, we've examined each component of the production system individually. Now it's time to connect them into a single engineering workflow. This is integrated nodal analysis, the framework used by production engineers to understand, diagnose, and optimize well performance. Think of this workflow as following one barrel of fluid on its journey to the surface. It begins in the reservoir, where the available energy determines how much fluid can enter the wellbore. That relationship is described by the IPR curve. The fluid then travels through the tubing, where pressure is continuously lost because of hydrostatic head, friction, and multiphase flow. Those losses define the VLP curve. Before the fluid reaches the separator, it must pass through the choke, where additional pressure is deliberately removed to control production and protect the well. Finally, the separator establishes the outlet pressure that completes the production system. Each component affects the next. Change the reservoir, and the inflow changes. Change the tubing size, and the lifting requirements change. Adjust the choke or separator pressure, and the entire pressure distribution throughout the well changes. The production system behaves as one connected system, not as independent pieces. When these components are analyzed together, the operating point emerges naturally. It tells us two things that every production engineer wants to know: how much the well will produce and what flowing bottom hole pressure is required to sustain that production. More importantly, it reveals the system bottleneck. Is production limited by reservoir inflow, by the wellbore, by the choke, or by the surface facilities? This is where nodal analysis becomes a decision-making tool rather than a calculation. Before changing anything in the field, engineers test different scenarios on the computer. They compare tubing sizes, evaluate stimulation treatments, adjust choke settings, reduce surface back pressure, and immediately see how the operating point responds. Instead of relying on experience or intuition alone, they make decisions based on physics. If there is one lesson to remember from this chapter, it is this: wells are never optimized one component at a time. They are optimized as complete production systems. The best production engineers don't ask, "How can I change this component?" They ask, "What is the bottleneck, and which change will move the operating point the furthest with the least cost and risk?" Answer that question correctly, and you've mastered the foundation of nodal analysis. Let's begin with a simple question. If every operator wants more production, why do we deliberately install a restriction at the wellhead? Why not remove the choke completely? The answer is that a choke is not installed to create back pressure. It is installed to control the entire production system. By regulating the pressure drop across the wellhead, the choke controls drawdown, stabilizes flow, protects the reservoir, and ensures the well operates within the limits of the surface facilities. Without that control, the well may produce aggressively for a short period, but not necessarily efficiently or sustainably. Now look at the nodal analysis plot. The reservoir inflow, represented by the IPR, does not change. What changes is the surface back pressure. As the choke opening increases, the pressure drop across the choke decreases, the required flowing bottom hole pressure falls, and the operating point moves along the IPR toward a higher production rate. Closing the choke has the opposite effect, increasing back pressure and reducing production. So why not always use the largest choke? Because production is only one objective. Excessive drawdown can accelerate reservoir depletion, increase water or gas coning, promote sand production, create unstable flow, and even exceed separator or pipeline capacity. In many wells, these consequences reduce long-term recovery far more than the small gain in short-term production. The production engineer's task is therefore not to maximize today's production. It is to maximize the value of the asset over its entire life. The optimum choke is the one that provides the highest sustainable production while maintaining reservoir integrity, flow stability, and compliance with surface operating limits. Every choke decision follows the same workflow. Analyze the reservoir, build the IPR, evaluate the VLP, test different choke settings, identify the new operating point, and select the setting that delivers the best balance between production, reservoir management, and facility constraints. Remember this principle. The choke is the production engineer's control valve. Its purpose is not to restrict the well. Its purpose is to manage the well. Suppose two wells are producing exactly the same rate today. Does that mean they are equally healthy? Not necessarily. One well may continue producing at that rate for years. The other may begin slugging tomorrow, load up with liquids, and eventually die. The difference is not the production rate. The difference is stability. Nodal analysis tells us where a well can operate. Stability analysis tells us whether it should operate there. Those are two very different questions. Let's start with the stable system on the left. Imagine the production rate drops slightly because of a small disturbance. As the flow rate decreases, friction losses in the tubing also decrease. The pressure required to lift the fluids becomes lower, allowing the reservoir to push more fluid into the well. The production rate recovers naturally. The disturbance disappears because the system corrects itself. This is called negative feedback, and it is the hallmark of a stable well. Now compare that with the gas well on the right. The same small reduction in production produces the opposite response. Gas velocity falls below the critical velocity needed to carry liquids. Water begins to accumulate in the tubing, increasing the hydrostatic pressure. The flowing bottom hole pressure rises, drawdown decreases, and production falls even further. Instead of correcting the disturbance, the well amplifies it. A small problem becomes a large one. This is positive feedback, and it is the mechanism behind liquid loading, severe slugging, and the eventual loss of natural flow. Notice what has changed. The disturbance was identical. Only the system response was different. Stable wells resist disturbances. Unstable wells amplify them. That's the defining difference. This is why production engineers don't optimize wells for maximum rate alone. They optimize for sustainable operation. The best operating point is not simply the one with the highest production. It is the one that combines strong production with pressure stability, adequate gas velocity to lift liquids, and enough operating margin to remain stable as reservoir conditions evolve. If there is one lesson to remember from this chapter, it is this: finding the operating point is only half the job. The real question is whether that operating point is stable. A well that produces slightly less but remains stable will almost always recover more hydrocarbons over its lifetime than a well pushed to an unstable limit.